right, Thermochem notes number 3. We're going to go ahead and talk about the heat equation. Okay, so we're going to talk about this idea of specific heat capacity. Now, normally, if I hadn't been sick yesterday, we would have done a lab that really showed you guys what specific heat capacity looks like in real life. What we're going to do is we're going to lecture on it first, and then tomorrow's lab will sort of give you a good idea of what specific heat capacity is all about. So we will talk about specific heat capacity today on paper and define it and show how we use it in problems numerically. But then tomorrow we'll put more teeth to that. And in general, notes number 3, this is putting a quantitative face on a lot of things we've been talking about. So we've done a lot of qualitative stuff. We're like, hey, energy is exiting or energy is entering our system, that kind of thing. These notes are going to start helping us be like, specifically, X number of joules, so a specific number of joules are entering or exiting our system. So we're actually going to put numbers to things. So we're going back to math, although it's not super complicated math. The specific heat capacity of a substance, watch what I'm highlighting, is the amount of energy needed to change the temperature of 1 gram of something 1 degree Celsius. So the amount of energy needed to change the temperature of something 1 degree Celsius. 1 degree Celsius. So if you want to make the temperature of something go up by 1 degree, you only have 1 gram of it, that's its heat capacity, the charge. So this is basically how cheap or expensive it is to heat or cool something. So not all substances are created equal. Some substances heat up really easily. Some take forever to heat up. They're not created equal. They're not created equal. The units for heat capacity, by the way, are joules per grams degree Celsius. Or if you want that written out with the numerator on top, joules over grams degree Celsius. And I sort of think of this as the currency of heat. It's like a price. So if you guys go to the deli, for example, they'd be like, okay, salami is X number of dollars per pound, and cheddar cheese is X number of dollars per pound, and turkey's X number of dollars per pound, okay? So everything has a specific price. And in the same way, every substance has a specific heat price to heat it up or to change its temperature, and that's a specific heat capacity. And so I just sort of think of it as a cost. So it's like a price tag. It's basically like a price tag. That's how you should think of specific heat capacity. It's like a price tag. A price tag for changing in temperature or something. Let me go back for a second. Right there. Here you go. It'll also be recorded later as well. Well, I'm recording it right now. Crazy. This is so meta. Okay. Now, if I want to eat mac and cheese right now, let's pretend I'm in my kitchen. I got the pot of water right there. I just set it on the stove. I've got my box of mac and cheese. Am I going to be able to eat mac and cheese in the next 60 seconds? Well, no, of course not. Because it takes forever to heat up that water, doesn't it? It takes forever to heat up that water. Have you ever thought about why it takes so long for water to heat up and start boiling? No, I've never thought of it. Well, it's because of water's specific heat capacity. So that price to change the temperature of water. So the reason why it takes water forever to heat up is because of its specific heat capacity. Now here's the number you guys are going to have to memorize. This is sort of like a section 9 type situation on MSDS, or the density of water being 1.00 grams per milliliter. This is just one of those numbers that you just want to know. The specific heat capacity of liquid water, so not to confuse it with ice or anything, a liquid water is 4.18 joules per grams degree Celsius. 4.18, 4.18, 4.18. 4.18. 4.18, 4.18, 4.18. So you look me in the 4 when you .18. Oh man, I'm just feeling like such a 4. And then also it was 0.18, and I was like, holy 4.18, 4.18, 4.18, 4.18. Okay? Burn that into your brain. You'll need to use this. I will put it on your first worksheet when you're practicing, but you will need to have this burned upstairs eventually. So if I were to put this, you don't have to write this out, but here's a sentence form of what 4.18 means for water. The amount of energy that it takes to heat up just 1 gram of water, just 1 degree Celsius, is 4.18 joules. So if I just have a little tiny gram of water, so if I were to show you guys what that looks like, that's probably several grams of water. That's a small little amount on my desk. Like, you don't need a whole lot to have a gram. So let's pretend this is 1 gram on my desk. If I want to heat that up just 1 degree Celsius, I have to pump 4.18 joules of energy into it. If I want to cool that down 1 degree Celsius, I have to take out 4.18 joules to cool it down 1 degree Celsius. Water has a super high heat capacity. It's really high. So it's more than ice, iron, copper, gold, brick, cement, rocks, dry soil, wood. Like, water's got a really high heat capacity. It's part of the reason why it's the elixir of life. It's compared, like to compare it, it's got like a heat capacity like 5 times higher than like a rock, which sounds kind of backwards, but that's how it is. Anyways, let's talk about our new equation. So we used to have density equals mass over volume. That was like the equation we used a lot in Unit 2. The equation we're going to use a lot in Unit 3 is this guy. It is Q equals MC delta T. Q equals MC delta T, sometimes known as Q equals MCAT. If you're a real dork like Damon, you'll draw whiskers on this thing, put a little face, and little pointy ears, and like, oh, there's a cat right there, right? Looks pretty good, you guys. Mr. Pilcher, how do you have so many good jokes? Okay. All right, there you go. There are 4 variables here, okay? Q, M, C, and delta T. What is Q, Mr. Pilcher? Well, that stands for the quantity of heat, of energy. It should always be more than 0. See how I have a little more than 0 symbol? It will be in joules. Boom. Capital J. So if I ever have a problem like, all right, so Emerson has 27 joules of blah, blah, that's her Q for that problem. Okay? Harry removed 617 joules. That's his Q for the problem. What do you guys think M stands for? Mass. What do you think the units for mass are? Grams. Mass in grams. Alrighty, C, that's that new term. That is your specific heat capacity. And again, those units are joules per grams degrees Celsius. If I want to write that a slightly different way, joules over grams degrees Celsius. So some people kind of like having that joules in a true numerator up top. And delta T is a change in temperature. Okay, should be in degrees Celsius, of course. And please note that one should always be positive as well. So we're never going to use negatives for our Q and T. Those usually indicate when energy is leaving the system. What we're going to do is we're just going to simply use our words to indicate the negative. So we're going to say energy is removed or energy is added to the system. So we don't need to worry about negatives. Just always go for positives on these. And we'll use our words to indicate the direction, which is what that negative symbol usually does. So basically what's going to happen is there are 4 variables. I will give you 3 of them and simply ask you to solve for the 4th one. So if I give you Q, M, and C, you're solving for delta T, so on and so forth. So on and so forth. Let me give you guys a quick little service PSA, service announcement. You go ahead and put your pencil down. I don't want you taking notes on this. It's just a basic thing. Hey, so for sig figs, I'm not grading sig figs at all this unit. Okay, you can consider sig figs a thing of the past for now. They may come back like once or twice throughout the school year, but it won't be for a while. All right, and they're not at all this unit. So if Ryan gets the answer 42.435, For now on, let's just go with a couple decimals. Okay, so just call that 42.44. If she gives me 3 decimals, I'm not going to take off points. I just don't want to have to look at this hot mess here with like 10 decimals. Does that kind of make sense? Just give me a couple. Like these guys down here, 23.25, 0.25. Now, if your first couple after the decimal are zeros, please give me those first 2 sig figs after the decimal. So don't call this 0.00. I do want you to call that 0.036. And 3.0, let's call that 3.00. Does that kind of make sense? I'm not grading sig figs. That's generally just what I'm looking for. Are those 2 sig figs? Okay, well, let's do a couple practice problems here before I let you guys go for the day. So here's a sample problem. How much heat energy is needed to raise the temperature of a 425-gram aluminum baking sheet from room temperature at 25 degrees to a baking temperature of 200? Okay, well, let's go ahead and find our Q's, M's, C's, and delta T's in this problem. Uh-oh. And then we will solve for whatever is missing. Okay, well, 425 grams, well, that is definitely a mass. Okay, so there's our M. I see some temperatures here too, 25 degrees Celsius and 200 degrees Celsius. Now the question is, which one do I use for my T? Is it 25 or 200? Answer is both. So remember, it's delta T, which means a change in temperature. That's what that little quote-unquote triangle is. So our delta T, I'll write that in a different color here, is your difference between your temperatures. So you're always going to take the bigger one and subtract the smaller one. So we want this to be positive. So that's going to be 175. So that's what we're going to plug in for our delta T. And then we're also given this number right here. Our specific heat capacity is 0.897 joules per grams degrees Celsius. So that is our C value. So if we're going to plug things in, it looks like we're looking for our Q. That's the one that we don't have, because this is our C. And which makes sense, because it says what is, or how much heat energy. That's definitely a Q when we're asking for a quantity of heat energy. So if I go ahead and plug everything in, Q, I'll just rewrite that because I don't know what it is, equals 175 times C, which is 0.895, or 897, I'm sorry, times delta T, which is our 175. And we don't even have to do any rearranging here. Oh, almost made a mistake. Our Q is not, I'm sorry, our M is not 400, oh my goodness. Our M is not 175, it's 425. I was kind of looking at 2 different numbers there. My apologies. So I don't even have to do any rearranging here. I can just go ahead and plug that in. And we should find that our Q is equal to 66,714.38 joules. And as the model student, I would always box that up so Mr. Pilcher knows what to grade for my final answer. Not bad, not bad. All right. Let's take a look at another problem here. What is the specific heat of a substance that absorbs 2,500 joules of heat when a sample of 1,000 grams of the substance increases in temperature from 10 to 70 degrees Celsius? Okay, well, I'm going to start identifying everything I have here. So it's asking me for the specific heat. We don't know that, and that's definitely our C. So that's what we don't know. So we should be able to find our Q, our M, and our delta T. Here's our Q, 2,500 joules. Our M is our 1,000 grams. There's an M right there. And our temperatures, so I have 2 temperatures again, 10 and 70. Which one do I use? Well, it's going to be both, because I want the delta T, the change in temperature, so it's going to be our big one minus the small one. It's going to be 60. So let's go ahead and start plugging things in here. Our Q is 2,500. Our M is 1,000. Our C, we don't know. And our delta T is 60. Now to simplify things, I'm going to combine my 1,000 here and my 60 right there. So rewriting this, 2,500 equals 60,000 times our C, which we still don't know. Now what do I need to do to both sides to get C by itself? So usually people are either going to tell me to divide by 60,000 or subtract by 60,000. Well, we have to think, It's currently C times 60,000, so we want to do the opposite of times. And that's going to be division. We would subtract the 60,000 if this was addition, so like C plus 60,000. But because this is multiplication, the opposite of that is division, not subtraction. So we're going to do both sides, divide them by 60,000. Just like that. These will cancel out here. And so 2,500 divided by 60,000 will get us our final answer. In this particular case, it's going to be 0.0, comes out to be 416, I believe, but we can just give that a couple of decimals. And this is a heat capacity, so it's going to be joules per grams degrees Celsius. It's going to be equal to our C. And again, I'm boxing that up because I'm the model student. Boxing it up, boom. There we go. Let's try one more together. Oopsie. Okay. What mass of hot water would it take to release 23,408 joules of heat into your body as it cools from 65 to the body temperature of 37 degrees? Okay, well, same process as always. Let's find our Q's, our M's, our C's, and our delta T's where they are in the problem. So first of all, it asks me for what mass. So it looks like M is what I'm looking for. That's what I don't know. So I'll have to be solving for that. 23,408 joules, well, that's definitely a Q. Your body temperature, we're given 65 and 37. So again, we're going to use those combined. We're going to find the difference to find our delta T. Okay. So delta T is going to be 65 minus 37. So 28 is our delta T. But then the question is, where's our C? What's our C value? We have an M is what we don't know. We have a Q. We have a delta T. But what's our C? Oh, this is the first time I've done this to you. It's water, right? And so never forget, that's your 4.18. That's that magic number, 4.18. Okay? So I'm going to go ahead and plug everything in here. My Q is 23,408. My mass I don't know, so just leave that as an M. My C is 4.18. My delta T is going to be that 28 degrees. That's the difference between my two temperatures. To simplify things a little bit here, I'm going to combine my 4.18, my 28. So rewriting the left-hand side here equals M times that 117.04. Now to get that M by itself, I'm not subtracting the 117.04 because it's being multiplied in the first place. I need to divide it. 117.04, 117.04. And so these will cancel out. And so 23,408 divided by 117.04 will give you my final answer. That's going to come out to be 200. And the units on that will be grams because this is a mass. And box it up. So we'll be doing a lot more practice with Q equals MC delta T in the coming days. But here's a good start for you.